Welcome to Mechanics and Materials. In this topic, we will explore how objects move, how forces affect motion, and how materials respond when forces are applied. We will study key ideas such as forces, energy, momentum, stress, strain, and the properties of materials. Mechanics and materials within the A-level specification. This topic develops students' ability to describe, predict, and analyze the motion of objects and the behavior of materials under forces, which is essential for later topics such as electricity, fields, and further mechanics. The specification emphasizes both conceptual understanding and quantitative problem-solving, requiring students to confidently apply equations, interpret graphs, and use vector mathematics. Key areas include scalars and vectors, moments, kinematics, Newton's laws, momentum, work, energy, power, and the bulk properties of materials. These concepts are not taught in isolation. Instead, students are expected to link ideas, such as understanding how forces cause acceleration or how energy is conserved during motion. Scalars, vectors, and vector resolution, moments, couples, and conditions for equilibrium. In mechanics, physical quantities are classified as either scalars or vectors, and understanding the distinction is essential for accurate modeling of motion and forces. Scalars have magnitude only, such as mass, time, energy, and speed, while vectors have both magnitude and direction, including displacement, velocity, acceleration, and force. Vector addition can be carried out graphically using scale diagrams or analytically using components, with calculations typically limited to two vectors at right angles. Resolving vectors involves breaking a single vector into two perpendicular components, usually horizontal and vertical, using trigonometry. This skill is particularly important when analyzing forces acting on objects on inclined planes, projectiles, or bodies in equilibrium. The moment of a force is defined as the product of the force and the perpendicular distance from the pivot to the line of action of the force. This relationship explains why forces applied further from a pivot produce a greater turning effect, a principle widely used in everyday tools such as spanners and door handles. A couple consists of two equal and opposite forces acting parallel to each other but not along the same line, producing rotation without translation. The moment of a couple depends on the magnitude of one of the forces and the perpendicular distance between their lines of action. The principle of moment states that for an object in equilibrium, the sum of clockwise moments about any point equals the sum of anticlockwise moments. Motion along a straight line and Suvat equations, interpreting displacement time and velocity time graphs. Velocity is defined as the rate of change of displacement, while acceleration is the rate of change of velocity. For motion with constant acceleration, the Suvat equations provide a powerful mathematical framework linking displacement, s, initial velocity, u, final velocity, v, acceleration, a, and time, t. These equations allow students to solve a wide range of problems, from objects falling under gravity to vehicles accelerating uniformly. A common application is free fall near the Earth's surface, where acceleration is equal to the gravitational field strength g, approximately 9.81 ms squared. Students are expected to select appropriate equations, substitute values carefully, and consider direction by assigning correct signs to quantities. Displacement time graphs show how an object's position changes, with the gradient representing velocity. A straight line graph indicates constant velocity, while a curved graph signifies changing velocity and therefore acceleration. Velocity time graphs are particularly important, as their gradient gives acceleration and the area under the graph represents displacement. This dual interpretation allows students to extract multiple pieces of information from a single graph. For example, a uniformly accelerating object produces a straight-line velocity time graph, and calculating the area beneath it reveals the distance traveled. Non-uniform acceleration results in curved graphs, requiring approximation techniques such as counting squares or dividing the area into shapes. Acceleration time graphs may also be encountered, where the area under the graph gives the change in velocity. Newton's laws of motion and free body diagrams, momentum, impulse, and conservation laws, work, energy, power, and efficiency. Newton's first law states that an object remains at rest or moves with constant velocity unless acted upon by a resultant external force, introducing the concept of inertia. The second law defines the relationship between force, mass, and acceleration, expressed mathematically as F equals ma. This law allows quantitative predictions of motion when forces are known. Newton's third law states that forces occur in equal and opposite pairs, acting on different bodies, a concept often misunderstood by students. Free body diagrams are essential tools for applying Newton's laws, as they help identify all forces acting on an object, such as weight, normal reaction, tension, and friction. Momentum is defined as the product of mass and velocity and is a vector quantity, meaning direction is significant. The principle of conservation of momentum, which states that in a closed system with no external forces, total momentum remains constant. This principle is particularly important in analyzing collisions and explosions. Impulse is defined as the change in momentum and can also be calculated as the product of force and time for a constant force. Force-time graphs are used to determine impulse by calculating the area under the graph, linking graphical skills with physical interpretation. Work, energy, and power are closely related concepts that describe how forces transfer energy and how quickly this transfer occurs. Work is defined as the product of force and displacement in the direction of the force, while energy represents the capacity to do work. The principle of conservation of energy states that energy cannot be created or destroyed, only transferred or transformed, and this principle underpins many mechanics problems. Power is defined as the rate of energy transfer or work done, measured in watts, and is particularly relevant in contexts such as engines and electrical devices. Efficiency is a measure of how effectively energy is transferred, calculated as the ratio of useful output energy to total input energy. Sankey diagrams are often used to illustrate energy transfers and losses visually. Density and bulk properties of solids, stress, strain, and Young modulus, required practical, investigating Young modulus. Density is defined as mass per unit volume and is a fundamental property used to identify materials and predict behavior such as floating or sinking. Bulk properties of solids include stiffness, strength, and elasticity, which determine how materials are selected for engineering and construction purposes. Stress and strain describe how materials deform under applied forces and are central to understanding material behavior in mechanics. Stress is defined as force per unit cross-sectional area, while strain is the ratio of extension to original length and has no units. The gradient of the linear region of a stress-strain graph gives Young modulus, a measure of stiffness that indicates how much a material resists deformation. A high Young modulus corresponds to a stiff material, such as steel, while a low value indicates a more flexible material, such as rubber. In this practical, students measure the extension of a wire under increasing load to determine stress, strain, and ultimately Young modulus. Accurate measurement of the wire's original length and diameter is crucial, as small errors can significantly affect results. The experiment requires careful application of forces, typically using slotted masses, and precise measurement of extension using a micrometer or ruler with a vernier scale. Summary of key ideas and examination strategies. In this topic, we have covered motion, forces, energy, momentum, and material behavior. To succeed in A-level physics, focus on understanding equations, interpreting graphs, and applying concepts to unfamiliar situations. Practicing exam questions is the best way to develop these skills. Thank you for watching.